Before I begin this episode, I just want to point out I've been saying operative system for the entirety of my first video and also in my code itself, but it's operating system. I really don't know how I made this mistake, but whatever, it doesn't matter. Anyway, also I want to point out the code for Redacted OS is now on GitHub. I will be linking it in the description and it will contain the code of everything we talked about in the first episode, everything we're going to talk about today, as well as more stuff that I have been developing since then. Eventually these videos will catch up to that. So last time we talked about how we were able to create an operative system in QEMU and use it to create a simple Hello World application running on the terminal, after which I used a GPU to get an on-screen console. But the truth is, we got up to this point and there's not a whole lot happening where we can call this an operating system. So today we're going to be looking into some of the features that our operating system needs to have and how we're going to be building them. Before we get to that though, I want to talk about the allocator that we created in the last episode. So in this allocator, we set aside a little bit of memory and then we just keep a pointer to it. And whenever someone requests memory, we give them the address that the pointer is currently at, and we advance the pointer by how much memory they have requested. And I mentioned that this is okay for the time being, but eventually we will run into a situation somewhat like this, in which some memory becomes available again, and because of the way that our allocator is built, we actually have no way of tracking that, no way of freeing memory, and no way of reusing memory. So I am going to talk about a proper solution for it, but before we get to that point, I'm going to say what I did quickly just to fix the problem as I was building something else. Then eventually I went back, revisited, and did it better. But I just want to point out this fix is a hack. Do not do this. It's just stupid. It's just something that took me 5 minutes to do in order to just move on to the next step, continue building what I was building, and then go back, revisit it, and do it properly. Essentially, what I did is I just created two different spaces of memory, a permanent one and a temporary one. In the permanent one, we will keep things such as the GPU vert queues, the memory that we use to communicate with the GPU. Considering the GPU will probably be active the entire time that our operating system is active, then we can assume that the vert queues are always going to be in memory. And then we have temporary memory. This is memory that eventually will no longer be needed. For example, strings can be stored in this memory. And so permanent memory works exactly the same as I mentioned before, as our allocator from before, but temporary memory can be reset. We can essentially just erase everything in it, put its pointer back at the beginning, and just reallocate that memory again. This technically works in that we are able to reuse that memory, but like I said, it's a hack. It's not a very good system for properly reusing memory because we're getting rid of everything that was in that memory. So we can only do it when we're sure that we can erase all that memory. So how do you actually do it? This is how I went back and redid it eventually in order to create a more robust allocator. And let's imagine that our memory looks something like this. We have some vert queues that are most likely always going to be in memory. We have some strings that at some point we'll probably not need anymore. And then we have some memory for some process running on the computer, which at some point may disappear, but for the time being has to stay in memory. Let's just say that our strings are no longer needed and we can now free them. Instead of simply deleting them, what we're going to do is we're going to write something called a free block. This is a structure that looks a little something like this. It is just a simple header that indicates how much memory we've just freed and also has a pointer to the next free block in memory. With that then, our allocator can simply keep a pointer to the first free block on this list. Okay, so how do we actually use this? Well, we start at the first pointer that points us to the first block. We will look at this first block and see if it has enough space to hold whatever we're trying to allocate. If so, then great, we just do the allocation there, we reuse the block. But if it doesn't, we just jump to the next free block, in this case block 2. We look at its size. If it's enough, then we've done the allocation. If not, we just go to the next point in memory. But wait, what happens if even that's not enough? Well, there are some fancy ways to fix this, but for the time being actually, this is very much a problem. If we run out of memory and we cannot allocate something, then this is probably an error. We'll call it a fatal error for the time being. This is essentially a problem from which our operating system cannot possibly recover from. Sometimes we call these panics. No, not at the disco, kernel panics. This is what it looks like in Windows. If you've used Windows, you've most likely seen this at some point or another, because Windows is
flipping amazing.
But this is what it looks like in Redacted OS. It's very much inspired by the one in Windows. So if we encounter a fatal error, such as for example running out of memory to allocate, then we just print a screen something like this to inform the user of what just happened, and we stop everything that we're doing. Considering this is an operating system that has a total of one user, then most likely I can figure out what went wrong and fix the issue. But what can I use to do that? How can I actually debug these issues? Well, that's where GDB comes in. And I did not know this is the logo for GDB. I think it's amazing, honestly. But GDB stands for the New Project Debugger, or GNU Project Debugger. This project has made me realize there's a lot of words that I've only read in writing, and I actually don't know how to pronounce them. But oh well. This is essentially a debugger that we will be using. And again, if you've done any level of programming, which most likely you have if you're watching a video about making an operating system, then you probably have used a debugger at some point or another. So specifically, we're using GDB, which is the debugger that we use for this type of project. And we're going to be using it with this command right here, which is very similar to the commands that we used to compile, link, and create our operating system in the first place. So how do we actually use it? Well, we need to run GDB, and at the same time, we need to run QEMU. So we need to run QEMU with these arguments. The first command and the lowercase s command allow QEMU to expect connections from GDB. In fact, I think they might actually be doing the same thing, but I'm not entirely sure, so I'm keeping them both. The uppercase s command is telling QEMU to not execute the program until GDB starts executing it. Then we can actually connect GDB to it using this command, which just connects the GDB instance that we have to the QEMU instance that we are running. Now, you may notice here I am using a file called kernel.elf or kernel.elf. Again, unsure on the pronunciation on that one. But we actually haven't talked about this file, though it's been there the whole time. Let's go back to our make file and look at it a little bit more closely. When we compile the .c, .s, or any other source files, we create a .o file. This is just a compiled version of them. But these are just individual files. They have no knowledge of each other. That's where the linker comes in. The linker takes in all of these .o files along with the linker.ld file that tells us how we're going to link all these files together and generates the kernel.elf. Finally, the obj copy command takes the kernel.elf and produces the kernel.img. So far, we've been executing this kernel.img file, but now we're actually going to start executing the .elf file. But what exactly is the difference between the two, and what is that last command doing? The obj copy command is taking the kernel.elf file and stripping its symbols. Not like that. Essentially, our kernel.elf contains a bunch of human readable information, such as function names or variable names even. But none of these are really useful when it comes to executing the program, and as a matter of fact, we actually kind of want to get rid of them, so it's a little bit harder to understand what our program is doing if you try to disassemble it. But also, mostly they're just useless information because the computer cannot really read these. So our obj copy file is just taking all of this and stripping them out, turning them into simple addresses for the kernel.img file. Essentially, the kernel.elf is an executable that has all these symbols, and the kernel.img is a raw binary executable that does not have all these symbols. The problem is, if we try to execute GDB using the kernel.img, we actually won't know what's going on because we won't have all those nice function variable names that we will use to orient ourselves when we're running the program and looking at its execution. Okay, so we're going to use the kernel.elf in GDB. But what exactly can we do with it? Again, if you've used a debugger, then you probably know the things that a debugger can do, at the very least the most basic things, but we're just going to go over them just to mention which functions I have used in the past that have helped me debug at some point or another. The main ones are probably breakpoints. So you just set a point in which the program's execution will stop. You can set this by just setting it at a specific function, such as the kernel main function, or by even setting it as a file name and file line, at which point it will stop exactly where you want it to. Now you understand why we want the symbol names to be there and not stripped out. Once we've actually stopped the program, we can actually use GDB to inspect memory. We can use commands like these to inspect specific instructions or values located at specific addresses in memory. And that way we can know exactly what it is that, for example, could be causing an issue that we encountered. And a little bit more higher level, we can also just print out the values of specific variables. Again, this is where using the .elf file comes in handy. And then we can continue the code's execution. We can either continue it so it just executes as normal, or we can even step instruction by instruction so we can see exactly what's happening and, for example, debug where a crash could be happening. And actually, at several points when I was developing my operating system, I found something like this happening. For whatever reason, our program's execution was now going to this address right here, 0x200. This is at the very beginning of memory, and it's really weird because we've already decided where the kernel is loaded, and the kernel is loaded at this address. So how are we going from that address to 0x200? Well, what happened is we triggered an exception. And when that happens, we will automatically jump to the address for the vector table, which is defined as 0x200. But what does any of this mean? Essentially, we've encountered a situation in which our program was stopped and we need to figure out why this happened and what we can do about it. Okay, but what's in the vector table? And how exactly do we handle this situation? And also, why does this situation happen? Well, the vector table looks a little something like this. We have 4 different types of exceptions that can be triggered, and each of them can be triggered by specific conditions being met. Actually, not all of them are a bad thing that happened. It doesn't necessarily mean that we encountered an error. Sometimes exceptions are expected and we can use them to our advantage. In fact, most likely in the next episode, we will be using these exceptions on purpose to help our operating system. Now, there's 4 different types of exceptions: the synchronous exception, interrupt, high priority interrupt, and system error. But before we look at what each of these mean, let's just say what exactly the vector table looks like internally. Well, we can define it actually as assembly with a little something like this. B sync handler. Now, B stands for branch. It's another way of saying go to. Essentially, our execution will go from 0x200 plus whatever offset for the current exception, in this case offset 0 for a synchronous exception, to a function called sync handler, which we will see later. Now, the synchronous exception can actually happen when the current instruction that we're executing caused an exception. Again, this could actually be something intentional, but for the time being, it's not. Essentially, an error happened when executing the current instruction. Let's take this instruction as an example. And keep in mind, this is pseudocode really, but the instruction that really causes an exception would be assembly, but just for simplicity, we're going to write it like this. Imagine that we're actually dividing by 0. As I think we all know, you cannot really divide by 0, so the computer doesn't really know how to handle this, and actually triggers an exception in this case. So while we were executing our program, we reached this line of code, and the computer didn't know what to do, so it jumped to 0x200 and caused a synchronous exception. We'll be talking about other types of synchronous exceptions later, and exactly how to identify them and what to do about them in a little bit. But before that, let's move on to talk about the other 3 types of exception. First is the interrupt. We are going to define its own handler, and interrupts are probably a subject that we will be talking about in depth in the next episode, so it's not something we need to talk about too much right now, but essentially these kinds of exceptions are triggered when something outside of our program's execution requires attention. One big example of this is user input. When the user presses a key, most likely an interrupt will be triggered so we can handle this as quickly as possible. Like I said, triggering an exception is not necessarily a bad thing. When the user presses a key, yes, we trigger an interrupt in order to handle that and not lose the input that the user just pressed, but then we continue the program's execution. And in fact, we want to do so in a way that the program doesn't even realize it was interrupted. After interrupts, there's also high priority interrupts and system errors, and the truth is these are not really used as far as I can tell. They're just there for compatibility with older systems, but technically, I did write handlers for them because I need them to be there for my vector table, but the truth is I'm not really using them in my code. And from what I could see online, they're not really used anymore. High priority interrupts just work as normal interrupts nowadays, and the system error specifically indicates maybe an internal error of the system that has essentially nothing to do with the code currently being executed or anything that has to do with the operating system, as far as I can tell. But for now, we're gonna ignore these. And at this point you may be wondering, wait, the table you said is at offset 0x200, so why exactly are you writing your own code for it? Well, the table is originally at offset 0x200, but this is actually determined by something called the vector base address register. This is a special register in the CPU that indicates where to jump to if an exception is triggered. Its default value is 0x200, but we can actually modify it to make it a custom address that we want. And so we create an assembly function that just defines where our handlers for each type of exception is going to be. And now, instead of jumping to 0x200, at which point we will not be able to know what happened to our system, it will jump to our functions, in which we will be able to interpret the exception, understand what happened, and maybe even recover from it. But how do we do that? Well, let's take a look at the two handlers that we are actually interested in, sync handler and interrupt handler. Now, the two instructions that I wrote for them are written in assembly, because this is how we need to write the table. But the sync handler and interrupt handler functions are actually C. So we can actually just write these in C and we don't have to care about assembly. Except I'm lying, we do have to care about assembly. We essentially need to read some values from 3 special registers to know what happened and know how to handle this exception. These are the ESR, ELR, and FAR. Let's look through them. ESR stands for the Exception Syndrome Register. Essentially, it just indicates what exactly happened. ELR is the Exception Link Register. It indicates which instruction was executing when the exception was triggered. If you remember about sync exceptions, I mentioned that these happen when an exception is triggered by the current instruction being executed. So that's what this register points to in that case. But in the case of an interrupt, we talked about how these are just events that happen that require the operating system's immediate attention. And so the operating system is taken away from whatever it's currently doing in order to handle this. The exception link register simply points to what the operating system was doing before that moment. So we can just go back there once we're done handling the interrupt. And then there's the fault address register. Sadly, there's no character named fault as far as I know. Although my dad used to call me. But this is essentially the address of what we were trying to do when the exception happened. I think it's better if I explain that with an example. So let's imagine we're running this code right now. Our current instruction is just trying to read a value from a pointer. But there's a problem with this. The pointer is invalid. In this case, our exception syndrome register, the one that tells us what happened, is going to be set to a specific value that we call a data abort exception. We will need to parse it and compare it against all known types of exceptions to know which one happened, and this way we will determine that it's a data abort. The link register will point us to the current instruction, the pseudocode for the instruction that I just showed. And the fault address register is going to point us to the data that we were trying to read, in this case, the pointer. So if we were to interpret it like this, it's telling us there was an issue reading data at the instruction that you were currently trying to execute, specifically at trying to read from the pointer. This was invalid in some way. But wait, what does it mean that it was invalid? If you've done any operating system development and you've gotten to this point, you know that if you try to read from 0, you will most likely just read either garbage or zeros. But what exactly does invalid mean in this case? Well, let's look at this scenario. We have our memory, and in our memory we have a bunch of stuff. We have the kernel code, we mapped the GPU like we did in the first episode to be able to communicate with it, and then let's say that we have a couple processes running on it. So let's say we're currently executing the second process, and it tries to access the kernel. It is actually a malicious process that is trying to override what the kernel is doing to try to take over the system. Or let's say that instead we have the scenario that I mentioned before, in which it tries to access invalid memory, something that really does not exist, like our pointer at 0. Well, we probably don't want to allow these things to happen, and this is where the MMU comes in. But what is the MMU? The MMU is the memory management unit, although right now I'm mostly using it as a memory protection unit, essentially just special hardware that takes care of the situations that I mentioned before so that we don't allow unauthorized access to certain parts of the memory. So let's say again we have our process and the process wants to access some data. Does it just directly access that data? No, the MMU gets in the way of that and prevents it from doing that. It only allows it to read data if it has permission to read that data and if that data is valid. But before we talk about this protection, I want to talk about another feature that the MMU has that is technically there, but I personally have not started using yet, and that is address translation. So remember our memory layout from before. We have the GPU, we have the kernel, we have 2 processes. Well, using address translation, we can actually just make one of the processes think that it is completely alone in memory. And not only that, but that is actually located at a completely different place in memory. On the left, we have physical addresses. Any memory address that we use is actually pointing to a specific place in memory. But on the right, we use virtual addresses. These are not necessarily real addresses, but we translate them into physical addresses, and that way we're able to access the actual physical memory. But why exactly would we want to do this? Why would we want the process to think that it is alone in memory, or even that it is located entirely somewhere else from where it really is, and then having to go through an extra translation step just to fix that? Well, the obvious answer to this is if it thinks it's alone, it cannot possibly access the kernel code or other process code. But also for practicality reasons, we can just make the process think that it has a lot more RAM available to itself than it really does. And all that thanks to virtual addresses. But again, I haven't really begun implementing translation, so I've barely just skimmed the surface of how it works. And once I actually implement it, I will be talking more about it, but for the time being, let's talk about the thing that we actually mentioned, memory protection. So again, we have our memory layout. We have the GPU, we have the kernel, and we have processes. Well, we probably want to prevent processes from accessing the kernel directly. And most likely we'll also want to prevent them from communicating with peripherals directly, such as directly with the GPU. Instead, we want them to go through the operating system. So to do that, we set up protection levels. We indicate that the GPU and the kernel are kernel-only access. They can only be accessed by our kernel itself. In the ARM architecture MMU, this is actually called privileged, but just for the sake of simplicity, I'm gonna say kernel only. Then we can define our processes as being kernel and process memory. Essentially, both the kernel and the processes can access this memory. And we do want this because the kernel needs to be able to actually allocate the processes, create them, control their execution, and even stop them from executing. So it needs to have access to their memory. And finally, any memory that we have left over, we're just going to consider unmapped. If we access any of this memory, it will also cause an issue in the same way that it would if we try to access kernel memory from one of the processes. And this is why the pointer at 0 actually was causing an issue, because it is in unmapped memory. But there is one more attribute we can set, and we can actually say that the GPU is device memory. What does this mean? Well, to explain it, I actually need to explain how the CPU accesses code. When the CPU wants to access memory mapped for the kernel, it can access it directly from memory, but this can be a little bit slow. So it also keeps a cache, essentially a faster version of that memory that it can quickly access. So when it's operating within a certain region of memory, it works a lot faster this way. There's a problem with this though. The cache is a copy of the real memory. And in the case of the GPU, this is memory that we are actually using to communicate with a device, which means we need to write to it, but we also need to read from it, because the device will be talking back to us. If we use the cache for this, we're using a copy of the memory. We're writing to the copy, and the device is writing to the real memory, which means we're probably going to be out of sync. So when we mark certain pieces of memory as device memory, we're simply saying they don't use the cache. Great, so now we know how we're supposed to do the mapping, but we don't know how to actually do it. So let's talk about translations and mappings. Now, in order to do all these mappings and even the translations that I mentioned before, we are going to use tables. Each of these tables represents increasingly smaller chunks of memory, going from 512 gigabytes for table L0, 1 gigabyte for table L1, 2 megabytes for table L2, and 4 kilobytes, which is commonly referred to as a page, for table L3. Now, these numbers technically can vary and depend on your configuration for the MMU, but this is how I configure them. And also, these tables are hierarchical. Each entry inside L0 will actually point to a different L1 table. Each entry in L1 will point to a different L2 table, and so on and so forth. When we're trying to translate an address, or even to map an address in the first place, we will read bits 36 to 30 of that address, and we will use that as an index within L0. Essentially, this is going to tell us where in the table L0 to look. There, we will find an entry, and that entry is going to indicate where the L1 table for that chunk of memory is located. We're going to repeat the same process for L1. This time we're going to look at bits 29 to 21, and we're going to use them as indexes inside L1. Again, we're going to use this index to find the entry inside L1, which is going to indicate where the L2 table is located for this chunk of memory. One more time, we're going to read bits 20 to 12 in order to get the index for L2. we're going to go to the entry that we found, and that is going to indicate where the L3 table for this chunk of memory is located. Finally, we're going to read the last 12 bits, which we will use as an index inside L3, and that will tell us the entry for the specific page of memory that we're reading. But before I explain what these entries look like, I just want to point out one thing when it comes to my project since it's now on GitHub. I did something a little confusing and called these tables L1 through L4. Instead of starting at 0, I started at 1, so technically L0 becomes L1, L1 becomes L2, and so on. It's a little bit confusing, but it should still be easy to understand. Okay, let's actually look at the entries. Each entry into this table is 64 bits and it's laid out like so. The empty parts are reserved and we don't really care about them, but let's go through each of these properties and see what they mean. First is UXN, which stands for Unprivileged Execute Never. Now, I mentioned it before and I will be talking about it more in a second, but we don't want our processes to have access to privileged parts of memory, so we call them unprivileged. In this case, the unprivileged execute never simply says that when we're running in unprivileged mode, then we don't want to allow that code to be executed. For example, our kernel code, we want to make sure that it cannot be executed from processes. BXN is similar to that, but it's specifically for privileged. It's privileged execute never. Essentially, when this is set, then the code cannot be executed in privileged mode, meaning the kernel cannot execute this code. Now, for example, we might want to make sure that our process code cannot be executed by the kernel. Then there's the address. Remember how we talked about virtual addresses and physical addresses before? Well, the translation process that we went through with the tables, we do that with the virtual address. And here we will find the physical address. That is how the translation is done. However, because I'm currently not doing translation, the virtual address and physical address are exactly the same. Then we have some reserved memory, and after that is the access flag. Now, this is actually something that I am not using at all, but it is used in some systems. It simply indicates if this memory has been accessed or not. When you're doing memory management, and for example, you need to free up some memory that's not being used, you may use this access flag to see if it has been used or not to decide whether to get rid of some memory or not. But again, this is not something that I'm doing, so we're going to ignore it. Then there's shareable. Shareable has to do with multi-threading, and to be completely honest, I've struggled enough with one single core to even start considering multi-threading. So this is again another field that I mostly just ignored for the time being, although I will probably have to revisit this one. Then there's the access permissions. Now, just like unprivileged and privileged execute never actually indicate whether different privilege modes can execute certain code, these access permissions indicate whether they are able to write or read certain parts of memory. So we can make some memory only readable by processes and readable and writable by the kernel, as for example would be the process code itself, so that the process cannot modify its own code. And this way we can also prevent our unprivileged processes from reading data in the kernel. Here we're simply indicating who has permission to read and who has permission to write. After that is a security bit, which again is not important to this implementation. And then the MAIR index, which stands for the Memory Attribute Indirection Register. Now, remember how I mentioned that some memory needs to be non-cached and some memory needs to be cached? Essentially, we're going to set up some policies for how to cache certain memories, and here we're simply going to indicate the index of which of these policies we're deciding. In my case, 0 is for normal memory and 1 is for device. Then we have the last two bits, the first one of which is the table bit. This simply indicates if this current entry is currently referring to a table or to an address itself. And this is where we go back to the physical address that we wrote and how we were traversing the tables before. In tables L0 through L2, essentially the first three tables, this bit would probably be set to 1, and it indicates that the current address points to another table. In the last table, L3, we would indicate that this bit would be set to 0, and it indicates that we're not pointing to a table, that this is actually the physical address that we were looking for. Essentially, we just traverse these entries until we find the one without the table bit. And that's where we found the address that we were looking for. And finally is the validity bit. This is simply set to 1 if the entry is valid or 0 if the entry is not valid. It simply differentiates entries that have been mapped to entries that have not been mapped. So just like that, we can do the mapping like we mentioned before. We can use the unprivileged and privileged execute never bits to decide who can execute certain bits of memory. We can use the access permission to decide who can write and read certain bits of memory, and we can use the MAIR index to decide which type of memory it is and how to cache it. But let's talk a little bit more about privileged versus unprivileged. So to do that, let's imagine a system that looks like this. It has a GPU, a mouse, a keyboard, and network access, but it does not have an operating system. And let's say that the user wants to install a bunch of stuff on it. So they install Fortnite, and they also have a document open with a bunch of sensitive information on it. Now, our document needs to access the GPU, the mouse, and the keyboard in order to allow the user to see the document and modify it. And Fortnite needs to access all the components in order to be able to play the game. But because we don't have an operating system, we don't have that layer of abstraction that I mentioned in the last episode, for example, in the GPU agnostic code, which means both Fortnite and the document app would both need to know which device they're communicating with and knowing how to drive that device. Essentially, each game, each program would need to have drivers for each specific GPU that it might want to support. And the same goes for mouse, keyboard, network device, and any other device that we include on it. But actually, the biggest issue that there is with this is the fact that there can be another process running, one that the user may not even know that's there. And it is also capable of directly connecting to some of the peripherals, as well as directly reading the memory from some of the other processes. So it can connect to your keyboard or your network or directly read the memory from the user's document app and steal that information that way. This is where the operating system comes in. First off, it includes that layer of abstraction that I mentioned before. So now each app does not directly need to communicate with each device on it. Instead, it communicates with the operating system, and the operating system then communicates with all the devices. But the operating system also sets up the privilege modes. Essentially, it gives itself privilege, and the processes running on it are considered unprivileged. Now, it has access to all the devices, but the processes no longer have direct access to them. So if our malicious process tries to, for example, access the network, it finds that it is unable to because of its privilege level. So at this point, it might actually try to override the kernel in order to give itself privilege, but even then, it finds that it is unable to do this. Now, of course, if you know anything about computer security, you know that there's ways around it. And honestly, even though I wrote the thing, my implementation of the MMU, I can already think of 3 or 4 different ways to bypass this, which I probably need to get around to fixing. Yeah. But by design, this is how it's supposed to be. Although, I have to be honest, there is one more major oversight that I have not taken care of, and it's the fact that technically this process can still access other processes' memory if it knows where those processes are in memory, which is pretty trivial to know. So yeah, this privilege level simply tells us who can do certain things on the system. Our operative system is capable of communicating with devices as well as with processes, but processes cannot communicate with devices directly. They need to go through the operating system. And the operating system has really opened one channel to communicate with it. You cannot communicate with it directly, but we will see that one in the next episode. Before we finish though, I want to make a little note about project organization. Now, in the past, we used to have our source files. These were the ones that we were using in the hello world. Now, of course, the project has grown significantly. There's plenty of other source files, but I'm just going to use these for the example. And then in the future, we might want to have processes. And so they're going to have their own code and their own files. But some of the code between the two could be shared. For example, types. And I haven't really talked about this, but throughout my code, you may have been able to see that I wrote things like uint64t, uint32t, which essentially indicates an integer of 64 bits or 32 bits. Now, these are actually defined in libc, the standard C library, but I'm trying not to use any libraries, so I just defined them myself. uint64 is an unsigned long int, and uint32 is an unsigned int. So I just did that in a header file, and that's the types.h file that I'm mentioning here. Well, like I mentioned before, we might want our user processes, even though they don't have privilege, to access this types file. But they don't need to access kernel code, and even if they wanted to, they wouldn't be able to do it. But just to make things a little bit more clear, I've actually divided the project into 3 subfolders. The kernel subfolder for all kernel stuff, the shared subfolder for the one that's shared between the two, and the user subfolder for user processes. Here I go again over explaining things that are pretty obvious. Oh well. So again, this is just a little explanation for what the project looks like internally. And speaking of the project's internal structure, you might remember that I mentioned that I created a file called boot.s, and that is s with a lowercase s. Now I've actually written another assembly file for our vector table that I mentioned before, and I created that with a capital S, so I decided to just change the name to boot.s with a capital S. But one big problem came from this. Essentially, I'm working on macOS, which is case insensitive and does not know the difference between a boot.s with a capital or lowercase s. So already, it didn't even recognize that I made a change. But what's worse is neither did Git, because Git also cannot tell the difference between the two. So at this point I thought, okay, so actually that doesn't really change anything. But it did change things, because make, which by the way has another amazing logo, does make that distinction. Essentially, when compiling, we do make a distinction between a lowercase and an uppercase s. And so they're actually seen as different files. And now this next part is probably not going to make any sense because it barely makes any sense to me. Maybe I completely misunderstood what the issue is, to be honest, but yeah, I'm going to explain it to how I understand it. Essentially, we have our .s files with a capital S, which create a .o file, such as boot.o. And then we have our .s file with a lowercase s, which also creates a .o file like boot.o. It seems like for whatever reason, if I make that change between the capital S and lowercase s and rename my file, then QEMU actually gets a little confused and seems to somehow read 2 boot files, and so it complains about duplicate symbols. Yeah, I really don't understand what's happening. So what's the solution to this? Well, I essentially just added a little note to remind myself not to change the extension, and I left it at that for now. The problem with this is, actually, we're running off of the boot.o that was compiled the last time that this whole thing actually worked. And so if I make any modifications to it, the problem will come back. Yeah, I'm gonna need to look into this issue eventually, but for the time being, I haven't needed to modify the .s file, so we'll keep it as it is. And just in case, I also set up a shrine where I pray to QEMU and to make nightly to make sure that they don't mess this up for me and that hopefully someday we will find a solution. And now we're hoping for the best. And if you don't mind, I actually have to go pray at my shrine now. So I'm gonna go do that, and next time we will be talking about processes. There's a lot to talk about, and even then we probably won't cover most of the things that I have done with processes, which again aren't even scratching the surface of all the things that you need to do in order to support processes in your operating system. But we'll get to that next time.